In the previous video, I derived this equation here, which I said describes the membrane potential, or the change in membrane potential, of a passive neuron with no active dynamics, but just leak channels and a sodium-potassium pump. And I mentioned that we had already encountered a differential equation of this type at the beginning. It's one of the first few videos that I did. So in this video, I'm just going to very quickly solve this equation. It's going to have the exact same solution, but just for continuity's sake, I'm going to solve it, and I'll try to keep it as brief as possible because I've already done this once. So I'm going to solve by separating variables, which I've done here, and then integrating both sides of this equation. So this is what happens when you integrate both sides. Remember that there is a negative sign out front here, and that occurs because you just need to remember the chain rule. And the only other thing that's slightly different here is I'm using, rather in previous videos I was using the letter C for the constant of integration. I just decided not to do that in this lecture, or this video, because C can also mean the capacitance of the cell, so I didn't want people to get confused. So here K refers to the constant of integration. So in this next step now I've exponentiated both sides. I've taken the -1 across before doing that, and because of our properties of exponents, I've dropped that constant of integration into the front. And the final step here is just to isolate the voltage, which is our dynamic variable that we're solving for. On the left-hand side, I've just reminded you that voltage is a function of time here, and this is the exact solution. And now the final step that we need to do is solve for what this variable k is, and we do that in terms of the initial condition. So the initial condition is the voltage or membrane potential at time 0, which here I've just chosen to be V0, which is just some constant. And just reminded you, so you plug in t equals 0 when t equals 0. This exponential turns into 1, which is, this term in the original equation over here turns into 1. And then if you solve, you get k equals VSS, the steady state voltage, minus the constant. Or sorry, that's completely wrong. That must have been confusing. The initial condition. So, sorry, I was going too fast there for a second. The constant equals VSS minus the initial condition. So after having plugged in the initial condition, our final solution looks like this. And if you think about this as t goes to infinity, then this term, this whole term here will go to 0, and we are left with VSS. So as time goes to infinity, we approach our steady state voltage, which makes sense. And on the other side of things, when t equals 0, then this here equals 1. So we're left with this expression here, and here this VSS cancels with this VSS, and we are left with V0. So this also makes sense. So at time equals 0, we start at our initial condition. And that's pretty much it for this lecture. If you're wondering what this solution looks like plotted over time, you can refer back to the previous videos that I've done, because it's the exact same solution. And I did a video that was looking directly at the time constant. Here the time constant is slightly different. It's equal to the resistance times the capacitance. So time constant is, you can think about it the same way, but now in this different application, we just have a different way of calculating it. And yeah, there's previous videos where I've already sort of dissected apart what this solution actually looks like, so you can refer back to them if you need to get a little bit more intuition about what this looks like. In the next few videos, I'm going to start expanding on this basic model, talk about how we can sort of build upon it to get more complex neural models. Thanks.